let me tell you a little bit about second-order optimality conditions. So I will show you this previous example here at this stationary point that was not a minimizer. So what we have here, we have the objective function, the gradient of the objective function, something along this line, and the gradient of the constraint, it was parallel to this. And but what we note that we have first order feasible direction here. There exists some d that walks inside the feasible set, so the gradient of the active constraint is less or equal to 0. But if I look at the second derivative of the function f, you see that this decreases. So in fact, at this point, I have something like this. The gradient of f x star transpose d is 0, and d transpose the Hessian of f of x star d is less than 0. So if I use second order approximation of f star plus d, this is something like f of x star plus the gradient plus this term. Okay, this is a more accurate approximation. So this is, I think we can consider this less or equal to 0, and this is less than 0, then the function decreases. Okay, so I have a feasible direction, and the gradient of f, it decreases. In first order it decreases, but in second order it also decreases. So if there exists some direction with this property, then you can rule out x star to be a minimizer. So this is a refinement of a necessary optimality condition. So under some conditions, if you have a local, if x star is a local minimizer, then you can prove that there exist Lagrange multipliers lambda I and mu j, but such that the Lagrange condition holds, the gradient is 0, but this also holds. This says that the Hessian of the Lagrangian, this is the matrix of second order derivatives of the Lagrangian function, this is semi-definite positive. So if you multiply d transpose by this matrix by d, this should be always greater or equal to 0, as long as d is some of these critical directions. So if I use first order approximation, what it says that there should not exist such directions. That should, at a minimizer, that there should not exist feasible directions that reduce the objective function. But this can happen because we are only looking at a first order approximation. So what a second order approximation says that for these critical directions, the Hessian of the Lagrangian should be positive. Okay? So if...
sorry, Gabriel.
¿Sí?
Sorry. Julio, dale al botón de grabar, porque si no los que están fuera no lo reciben.
Yo creo que ya está grabando.
No.
Yo lo estoy viendo en mi ordenador.
Ahora sí. Ahora sí. Vale, ahora sí. Vale, perdón.
Nada.
Hasta luego.
Should I continue? Okay, so I want to mention something about the history of nonlinear programming. So, as I said at the beginning, it started with this work of Kuhn and Tucker in 1951. So in 1948, with Gale, they did the work on the duality of linear programming. So they thought that they could extend their analysis to nonlinear programming problems. So Tucker, he was a professor at Princeton. His main area is topology. And Kuhn was a PhD student in algebra. So they met for some reason, and they did the linear programming duality, and then Tucker invited them, Kuhn and Gale, to do this paper on nonlinear programming. So Gale was very busy at the time, and he declined the offer. So the paper the work was done only by Kuhn and Tucker. And Kuhn built his career in Princeton, and he worked on game theory and optimization. He did only his PhD in algebra. And in this paper, they exploit this saddle point structure. So since they were building on the work of von Neumann, he was a specialist on game theory, their approach to duality was using this saddle point problem. So this function phi here, it's the Lagrangian function. So you consider here the problem only with inequality constraints. So you have only Lagrange multipliers mu associated to the inequality constraints. And what they proved was that at this point, x star, mu star, the Lagrangian function has a Nash equilibrium point. Is that right, Julio? This is a Nash equilibrium. For if you fix mu star, x star is a minimizer of f. If you fix x star, mu star is a maximizer of phi. So this is a Nash equilibrium point, and for us in optimization we call this saddle point. So it's not a minimize. If you look at x and mu as a single variable, you have directions that increase the function, and you have directions that decrease the function. So it's a saddle point. So they studied conditions for this problem, and exploiting this structure, they were able to prove the KKT condition. And he died this year, in July, and he had a career in game theory and optimization. Okay, that's it about Kuhn-Tucker. But as I mentioned in the beginning, this condition is known as the KKT condition. The first K is by Karush. So it's Karush-Kuhn-Tucker conditions. And what Karush has to do with this theory. So Karush was a master student in the Department of Mathematics of the University of Chicago. And this department was known for problems with calculus of variations. So it's the optimization problems, but the variables are not an n-dimensional vector. It's an infinite-dimensional vector. So you want to find functions that minimize some energy, and so this is what the department was known as. And the Karush thesis was about this of functions of several variables with inequalities as side constraints. So he studied these simpler problems on their view with a finite number of variables and with inequality constraints. And he proved everything that Kuhn and Tucker did, including first and second order conditions. He also did that. And Kuhn and Tucker, they had a lot of visibility since linear programming was so useful, and military research, the military program of the United States was investing a lot of money, so Kuhn and Tucker had immediately recognition because of their work, and Karush was unknown. So in 1975, so 24 years after the first paper of Kuhn and Tucker, Kuhn discovered the work of Karush. So he wrote to Karush asking about the history of his discovery, and he wanted to know why Karush didn't say anything, why he was so quiet this whole time. So Karush answered with this phrase. He said that some colleagues wanted him to say to the world that he did what he did before. So he said that he analyzed the situation and looked at the paper, and he concluded that Kuhn and Tucker had exploited and developed this subject so much further than I, that there was no justification for my announcing to the world, look what I did first. So he didn't say anything. So in fact, Kuhn and Tucker had more deep results concerning the duality also, and this approach by saddle point. So Karush's work was done before, but okay, he didn't want to say this. And it's interesting that Karush and Tucker, they worked together at the Manhattan Project, the nuclear bomb project of the United States, and he knew Tucker, and he never mentioned that he had done this before. But another thing is that his thesis dissertation was never published, so it was only known for for people that were at his department. So this was difficult to. This is one reason why nobody had known his condition, and another reason is that at his department they thought that it was not it was not relevant because they were interested in the infinite dimensional version of the problem. So his thesis were considered a more marginal result, and in 1939 no one could predict that this could be useful in the future. And it's interesting that Kuhn, he always had this willing to investigate the history of the subject. So he wrote a lot about the history of nonlinear programming, and he is also known for other important works in operations research. In particular, he's known for the Hungarian method for assigned distribution. So you have some tasks that you need to be done, and you have some workers that can perform these tasks. So this Hungarian method, it gives a way to assign these tasks to the workers, and it's a very well-known method. And Kuhn discovered this method too. And recently, I think it was 2012, at an Euro conference, Kuhn announced to the world that this method was known 100 years before his publishing. So And so he investigated how, I don't remember who solved this problem before, but so it's interesting that Kuhn investigated this subject too. So another important name in the history of nonlinear programming is Fritz John. So Fritz John, he did his PhD in Göttingen and under Kuhn. And when Kuhn came to New York, Fritz John came with him. And he published his paper in 1948. So it's also before Kuhn-Tucker. And his paper is Extremal Problems with Inequalities as Constraints. So at this time, he had had his PhD by 15 years. So he was a well-known researcher at NYU. He worked on partial differential equations, convex geometry, and nonlinear elasticity. So there is also a well-known book for PDE by Fritz John. But in this paper, he was studying convex geometry. So this is what Fritz John was studying. So you have here a bounded set S. In our case here, it's this unit square. And one problem was to find the smallest sphere that contains the set S. So you can ignore for a moment the inner sphere. So the outer sphere is the problem that Fritz John was trying to solve. Find the smallest sphere that contains the set S. So his approach to this problem was to formulate this optimization problem. So you have variables x1 to xm. This is the dimension of the space. And this corresponds to the center of the sphere that you are trying to find. And you have this xm plus 1 that correspond to the squared radius of this sphere. So you have to minimize this radius. Okay, xm plus 1 is the objective function that you need to minimize. And the constraint is that the sphere contains each point of S. So if you put this to the other side, this said that for every point y for every vector y in the set S, if you measure the distance of the center of the sphere to this point y, this should be less than the squared radius of the sphere that you are looking for. So this says that S is inside the sphere. So this is almost an optimization problem in the sense that we defined. The difference here is that S, for every point y in S, you have a constraint. Okay, so but S may have infinite points, infinite number of points. So this is in fact a problem of optimization with an infinite number of constraints indicated by this vector y. So this is how Fritz John formulated his problem, and he was able to develop first-order optimality condition to this problem, and these are precisely the KKT conditions. And using this technique, he was able to prove this other result, that if your set S, now this triangle, is a convex set, in fact, yes, the set S is a convex set, and then you can prove that you can always find an ellipsis here, outside and inside the ellipsis, such that these ellipses are homothetic. So this means that they are similar. So if you You have the smaller ellipses, the larger ellipses you can get by augmenting it proportionally through its center. So this is what's called homothetic ellipses. So they are similar in the sense of Euclidean geometry. And the ratio of similarity is less than or equal to the dimension of the space. So he proved that you can put two similar ellipses and with ratio less than or equal to n, and the inner ellipsis lies inside the convex set, and the outer ellipsis lies outside the convex set. And in fact, the outer ellipsis can be taken as the least volume ellipsis containing S. You can use the first problem and replace the sphere by an ellipsis and do the same formulation, and you can find this outer ellipsis, and if you make this ellipsis small, you find this inner ellipsis that you can always prove to exist. And this is well known in convex geometry. This inner ellipsis is called John ellipsoid. Okay, so John condition is a little bit different in this sense. For the KKT conditions, we have this. I will put here only inequalities. Okay, this for the active constraints. And to prove this KKT condition, you have to impose some condition on the gradients of G. That's what we call a constraint qualification, and we will study this further. But John condition included here a multiplier for the objective function. So this mu0 is always greater or equal to 0. And if you include this, that is, if you allow this multiplier to be 0, you can prove this without any constraint qualification. So this is what John did. And Kuhn and Tucker, they did this also. They proved this result first, and they incorporated a constraint qualification to prove that mu is positive, strictly positive. So if some constraint qualification, some condition on the problem holds, you can prove that mu0, you can take it to be 1. Then the KKT condition holds. But otherwise, if this CQ does not hold, you have this nice property, and you can take mu0 equal to 0. Of course, this vector mu0 and this should be non-zero. If you take all scalars to be 0, you have a trivial solution. But the Fritz John result says that you have a non-trivial solution to this problem. So this is known as Fritz John conditions, and this is important also. Okay, so let me show you an application. I will use here the KKT condition to prove the law of diffraction, Snell's law of diffraction. In fact, it's a problem with only one inequality constraint, so it's more an application of the Lagrange theorem. So this problem, you have a point here, y, and you have a point here, z. And you have here the boundary of a surface, so it may be a nonlinear surface. So maybe this is air, and this is a glass, a curved glass. And you have this function, h of x equal to 0, that measures this boundary of this surface. Okay, so I want to, at this point y, I want to know how light travels from this point y to this point z. So the light travels here linearly, and in some point here, x star, its angle changes and it goes to z. So what I want to know is to find this point x star, where the path that the light will follow this path. Okay. So the idea behind this method is that light will do this in the minimum time possible. So I can compute here for each x along this curve. So if I point here, if I mark here a point x, this will be a feasible point for my minimization problem, and light would go from here to here and here to here. Okay. So I want to know which is the point along this boundary of the surface that when I compute the time that the light takes to make this path, it's the minimum possible. So you have this angle. Here we have the normal to the tangent to the surface and normal to the surface. Snell's law says that if you have this angle, theta y, and this velocity of light, vy, and here theta z, velocity vz, this is the law of diffraction. Okay, you have also a law of reflected light, that the reflected light will reflect with the same angle, and you can use this same principle to prove this. So the idea is to solve this minimization problem. You have this function t of x. It's the time, depending on where you mark the point x on the boundary of the set. And this measures the time light takes to travel from y to x. So I can measure this distance from y to x, and I can divide it by the velocity of light on this side of the glass, on the air, and this is the time the light takes to perform to walk this distance, and this is the time light takes to go from x to z under this velocity vz. Okay, so this is the function I want to minimize. So at a solution x star, what I have is that the gradient of the objective function that you can compute like this should be parallel to the gradient of the constraint. Okay, this is what the Lagrange condition says. The gradient of the function is parallel to the gradient of the constraint. And note that the gradient of the constraint lies somewhere at this point x star. It is parallel to this normal line. Okay, the gradient of the constraint is perpendicular to the level curve. So the normal is given by the gradient of the constraint. So what I have here is that the gradient of the constraint, it lies along this line of the normal line, this gradient t. And I can compute this in this way. If I define these other vectors, y bar, z bar, it's defined in the way that this is y minus x star. So this is a scalar multiple of x star minus y. So I will mark here as y bar. It's a scalar multiple of y minus x star. So it's somewhere around along this line. And z bar is somewhere along this line, z minus x star. So it's chosen in such a way that when you add these vectors, you have minus the gradient of the time function. Okay, so In fact, I can build this parallelogram here. I have x star y bar, x star z bar. So if I add these two vectors, I have the minus the gradient, and this is exactly the diagonal of a parallelogram here. So I can draw here parallel lines. This is parallel to this, and this is parallel to this side here. So I have a parallelogram here. And minus the gradient of t is exactly the diagonal of this parallelogram, and I know at a solution that this must lie exactly at the normal of the surface. So that's why I made this picture in this way. Okay, so I simply use now triangular similarity to show the law of diffraction. So by a triangular similarity, so I see that this half of the parallelogram is similar to this one, or I can see that this triangle here is similar to this one. So in particular, what I want to use is that this distance here, can you see? Okay. This distance here, it's the same, here and here, by a similarity of triangles. So I can simply compute this distance. So this distance is this side, x star minus y bar, times the sine of this angle, that is theta y. So this is this side, and this should be equal to this side here, and this sine of this other angle, that is theta z. So you have this equality here. And then if I use the formula for y bar and z bar, and I compute this side of this vector, it's somewhere around here. This is y bar minus x bar. If I compute this norm, this numerator cancels with this denominator. So I have 1 over Vy. So 1 over Vy times sine of theta y equals 1 over Vz sine of theta z. So this is exactly the law of diffraction. Okay, so we used here that the gradient of this time function lies along the normal of the surface. So this is precisely what the Lagrange multiplier condition says. Okay? All right. So I want to briefly mention two ways to solve an optimization problem. So it's the external penalty method and the internal penalty method. So the idea here is I have this constraint optimization problem, minimize f, subject to equalities h and inequalities g. But I don't know how to solve this problem numerically on the computer. What I know how to solve is a non-constrained problem. So if I have minimize a function without constraints, I can solve this using Newton method, gradient method or something like that. So I want to write this constraint problem as a non-constrained problem. So an idea to do this is to use penalization. So we define this function p of x. It should be a smooth function. It should be always non-negative, but this is an important condition. If you have a feasible point, this penalization is 0. And this characterizes p of x equals to 0, characterizes a feasible point. So in a feasible point, this penalization function is 0, and in an infeasible point, this is positive, greater than 0. So what we can do is minimize this combination of the objective function with the penalization function. So note here that if I have an infeasible point, the objective value would be f of x plus this constant ρ times this positive value. So if I take ρ very large, so we take in fact we take a sequence of parameters ρk that goes to infinity. So if I take an infeasible point x, this p will be positive, and these terms ρk will penalize the objective function. I will have a very large value here. So the solution of this unconstrained problem will automatically find points where p of x is equal to 0. Because at points where p of x is greater than 0, we have a very strong penalization constant here that makes this function very large. So with this simple idea, we can transform an unconstrained problem to we can transform a constrained problem to a sequence of unconstrained problems. So what we have to do is increase ρk at each iteration and solve this problem. Okay? So you can now build a sequence of solutions, xk. So we have here these problems: minimize f of x plus penalization term times p of x, and this is a unconstrained problem. So when I solve this, I get a point xk. Okay, so for each k, you solve this problem, and when you increase k, you increase ρ. So ρk is a sequence, increasing sequence that goes to infinity. So what we will prove is something in the lines of this sequence of points xk converts to the solution x star. So in practice, you may think that you can solve only one problem at this time. So you can take ρk. Sorry. You can take initially a factor, this number ρk can be very large, and you can solve one single problem, and this will be the solution. But in practice, this is very hard to do, and for two reasons. If you start with ρk very large, this problem is very difficult to solve. Okay, because computers don't deal well with sequence that goes to infinity. So these problems are very hard to solve in practice. So if you start with a small value of ρ, you can find a solution x, and this solution x will be a good starting point to the next optimization problem. So you increase a little bit ρ, and you can improve your approximation to the solution x to xk to another one xk plus 1. And this is the computer can deal well with this. If you have a good starting point, you can solve this difficult problem with ρ very large. So that's why you have to solve a sequence of problems, because a computer deals well with this. You have a good starting point for the next optimization problem. It's the solution of the previous one. In fact, you can prove that if you use a specific function p here, you have you can use a finite value of whole, and you will find the solution of the problem. You don't have to solve it making whole k to infinity. But the problem is that this penalization function is non-differentiable. So it's hard to solve each subproblem. But one idea is to use this differentiable penalty function. So the norm is non-differentiable, but if you square it, you have differentiability. And here the maximum is non-differentiable, but if you square it, you won't have any problem. So this penalization function fulfills these conditions with a smooth function. So you can use smooth techniques to solve unconstrained problems under this condition. So this is the theorem I was mentioning, that if fxk is well defined, so xk is the solution of this problem with a fixed whole k. If you can solve this problem and then you generate a sequence xk, what we can prove is that xk is a global solution to the problem of minimize p of x. So p of x is this function that is zero if and only if x is feasible, and it's non-zero if x is infeasible. So what this theorem is saying is that if your problem has a feasible point, if there is some point that is feasible, when you generate this sequence, you will converge to this point, to this feasible point, where p of x is zero. It's the global minimizer of this function. If your problem is infeasible, you don't have any feasible point, you can use this algorithm. You won't converge now to a feasible point, but you will converge to a point that minimizes infeasibility. So even for problems where there are no feasible points, you can use this method to generate a point that is almost feasible in some sense. Here there is one technicality that you can't prove that this sequence converges, in fact. You can have two different accumulation points, but what we proved is that each of these accumulation points must be a feasible point in case it exists. Okay, so another thing that we can prove is about optimality of this algorithm. So typically, an optimization algorithm will have two theorems in the way this one is presented. The first theorem will deal with feasibility of the problem. So you have something like this. You generate a sequence, and limit points will be minimizers of an infeasibility measure. So this is what we have in many optimization solvers. And so if the problem has a feasible point, you will have a feasible point. But you can't prove that an algorithm generates feasible points. This is impossible because a problem may not have feasible points. And here about optimality. So if this sequence is well defined and there is a feasible point, there is a point P, a point where P vanishes, the feasible region is non-empty, then you can prove that every limit point of this sequence is a global solution of the original problem. Okay, so we can prove this for this very simple algorithm. And in fact, we will do this in the next lecture.
Excuse me, just one question concerning this second theorem. So here you're saying that you're getting a global solution because you are implicitly assuming the previous slide that you are able to solve globally each one of the steps. But that, of course, in general will be also a problem. You may only obtain local optima each step. You can convert result here for local?
Yes. here I said that this xk is a global solution to this problem. So this is difficult in practice. So what we will do in the Augmented Lagrangian, that is a practical implementation of this idea, is that in fact we will only find a point, a stationary point of this subproblem. Okay, so what we will prove is that it is a stationary point of the problem. Okay, I don't know if you can prove this on this framework. I know on the Augmented Lagrangian framework, this is true. But if I ask here local solution, I don't think I can prove here local solution of, you won't converge to a local solution. But on some conditions, on some specific framework, this is what it's done. So, but this property is important because if for your class of problem you are able to solve it globally, unconstrained, you will converge to the global solution of the constraint problem. So this method can be used as a theoretical tool to prove the KKT conditions, and that's what we will do. We will prove these two theorems and use it to prove the KKT conditions. But this can be adjusted to be an efficient algorithm, and this is the Augmented Lagrangian. Okay, this is one example of the external penalty method. So we have this objective function with two variables and two constraints. So what we do at each step, we minimize this penalized function. So it's the objective function plus whole k times the infeasibility measure. So let's call this phi k of x. And at a solution xk of this problem, in fact, you have the gradient of this unconstrained problem will be 0. So if we solve this equation, we have this formula for xk. It's the first variable, x1, is whole k divided by 1 plus whole k, and the second one is 0. And we see that this is converging to 1, 0. That is the solution for this problem. Okay, the only feasible point here is x1 equals to 1, and x2 less than or equal to 1. So since we want to minimize this term, the least value is x2 equal to 0. So this is converging to the global solution that is 1, 0. But we note here that in order to get convergence to the solution, you have to make whole k go to infinity. If whole k is not infinity, you won't be at a solution. Okay, so this is a problem that for implementation you should take into account. So let me see if this works. It's a very simple video. This is the level curves of the unconstrained problem. So it is this at whole k equals to 0. You have the level sets are circumference, x1 squared plus x2 squared. They are constant along these lines. And this is the point 1, 0, that is the global solution of the problem. So if we start at a whole k small, you have this point here, this is the global solution. This is the smallest level set of this function. So as you increase whole, you have this effect of elongating these level sets. So you see that the solution now is closer to the solution of the problem. And okay, this is what you get as whole is larger. So we see that this problem has these elongated level sets. So this is hard for a computer to solve. If you have this is associated to the eigenvalues of the Hessian of the function, objective function. They have a very large eigenvalue and a very small eigenvalue, and this makes it difficult to converge to a solution. And in particular, if you use a gradient method, if you start here and you walk along the gradient of f, you will go somewhere around here, and you have this behavior of zigzag behavior. So gradient interaction will walk towards the solution. It will walk perpendicular to the solution. So the gradient direction is not a good direction when you have elongated level sets. So this makes an optimization solver difficult. So we don't want to have whole k too large. Okay. So we will see this method in much detail on the next lectures, but for this lecture, I would like to end with this internal penalty method. That is the basic ideas for the interior point method that I mentioned before. So this is a similar idea. So for the external penalty method, you walk along infeasible points, and you penalize the fact that this point was infeasible, and then you converge to a feasible point. For interior point methods, you do the opposite. So let's assume that we have a feasible point, an initial feasible point x, that is inside the feasible region, and what we want to do is to generate a sequence that do not go outside the feasible region. So we put a barrier at the frontier of the feasible region. So this is the function b, a smooth function, non-negative, but it should have this property. If you approach the frontier of the feasible set, so you have a feasible sequence x converging to some place, and this function gi of x is converging to 0. So you are converging to the frontier of the feasible set. This barrier function should go to infinity. So since you are minimizing here a combination of the objective function and the barrier, you won't get out of the feasible region. But since the solution is typically on the frontier of the feasible set, you must have this penalization parameter mu tends to 0. So you will find, you will be able to find a solution on the frontier. And a typical barrier function is the log barrier function that has this formula. You see here that if gi converges to 0 from a negative value, you have plus infinity for bx. So this is the log barrier function. And you can use this for nonlinear optimization, for general nonlinear optimization. But if you use it for a linear program, so minimize C transposed x times subject to ax equal b, x greater or equal to 0. This is a standard form linear programming problem. Let's examine on more details this method. And here, in fact, you can do this analysis for a convex quadratic problem.
Gabriel, it's already 2:03, so if you want to take, you can take a couple of minutes, but we are almost out of time.
Ah, okay. I thought it was 2:30 for some reason, but we can end it here.
Okay, so then we stop here and we continue with interior point tomorrow.
Okay.
Okay. Bueno, muchas gracias y nos vemos mañana a la misma.